Welcome back to this module on tides. This second part will help you finish the pre-lab exercise. We're looking back again at that tidal curve for the month, and one thing that we want to try to understand now is why the range of the tides varies with the phases of the moon. For example, notice these days around the full moon that high tides are quite high and the low tides are quite low. And then you go over here to where we have the new moon, and you can see again very high tides, very low tides. But if you go in the in-between times, you can see that the tides are more muted. There's not a very high tides, the low tides are not very low. In other words, the tidal range is less here, and the tidal range is greater here and here. And the reason for that has to do with something we haven't thought about yet, which is the fact that the sun also pulls on the ocean, and it also makes bulges of water. Take a look at this figure here because it separates things a little bit better. You'll notice that there's a bulge of water facing the sun and a bulge of water away from the sun. So in other words, the sun creates bulges like the moon does, but they aren't as big as the moon's bulges. Now the key thing here is that if we get the sun's bulges and the moon's bulges to line up, it makes the total ocean bulge more. And so as the Earth spins under these extra large bulges, we see extra high tides and extra low tides. This lining up of the bulges happens during what's called the new moon and the full moon, when the moon is either between the Earth and the sun or on the opposite side of the Earth from the sun. And so if we go back to that previous figure, you can see the high tidal range is occurring during the full moon and the new moon. But 7 days after the new moon, the Earth moves to this position, what we call the first quarter. And 7 days after the full moon, the moon moves to this position, what we call the third quarter. And in either of these positions, the bulges of water made by the moon are out of line with the ones made by the sun. And that results in less of a tidal range. There's less of a change, less of a change between the high tide and the low tide during what's called the first quarter, or what's called the third quarter, sometimes the last quarter. Now another factor that controls the range of the tides is how close the Earth is to either the moon or the sun. The orbit of the moon around the Earth is not a perfect circle, it's an ellipse, and the moon is actually closer to the Earth during certain times of the month, and we call it perigee when the moon is closer to the Earth, and apogee when the moon is farther from the Earth. And as the Earth orbits the sun, it doesn't follow a perfect circle, it's also an elliptical orbit. And during the time when the Earth is closest to the sun, we call that perihelion, and it happens in January. And we call it aphelion when the Earth is farthest from the sun, and that happens to be in July. The key idea here is that the closer the Earth is to either the moon or the sun, the stronger the gravity is going to be pulling on the ocean, and the bigger the bulge is going to be. In other words, the larger the change of the tides, the bigger the change from high tide to low tide. Now, one final factor that we need to think about is how the tides actually move as they move around an ocean basin. This bowl of water here mimics an ocean basin, and the movement of the tide around the ocean basin actually follows what we call a rotating wave, and that's what this video is illustrating. The water sloshing around in the bowl here actually mimics the way that the tide rises and falls as it moves around an ocean basin. So the edges of the ocean basin would represent shorelines. And if we were to put a marker here into the water, which I'll do right there, if you're standing on the shoreline right there, well, what you're seeing is the tide rising and the tide falling. But the actual movement of the wave that the tide makes is a rotary pattern. And there's a point in the middle of the bowl where the water doesn't go up or down at all. And we call that an amphidromic point, a place where there is no tide. And what we find is that the tide can rotate around the ocean basin, around that amphidromic point, in a way that we're going to try to figure out. So during the last part of the lab, we're actually going to go look at the North Pacific Ocean, and we're going to try to figure out what the tide is doing in this ocean basin. We're going to try to figure out, is it sweeping around this direction, counterclockwise, or is it sweeping around clockwise? And the way we're going to do that is we're going to zoom in on the coast of North America, and we're going to gather some data for 4 stations. One down near San Diego, one maybe up in Northern California, one in, Oregon, and maybe one up in Washington. And we're going to look at the timing and the height of the tides as they move past the west coast of the United States. And we'll try to figure out what the tide is actually doing, which direction it's rotating. So with that information, you can finish your questions on the pre-lab and enjoy your day in lab.